1 of section 1-2, functions and graphs. In section 1-2, part 1, this is what we're going to be talking about. Our learning goals are identifying domain, the independent variable, and the range, the dependent variable, from either an equation or a graph. We're going to use inequality and interval notation interchangeably. We're going to view and we're going to interpret some graphs, and we're also going to talk about odd and even functions, both from the equation and from the graph. So let's get started. Okay, first, independent and dependent variables. When we're talking about functions, we discuss what is the independent and what is the dependent variable. The independent variable most typically is the x variable, and the dependents are the f of x's, which we oftentimes call y's. And the independent variable, the x's, are what we call the domain, and the dependent y's or f of x's are what we refer to as the range. Okay, so now we're going to talk about what is a function and what is not a function. So this mapping represents a function. You can see here is our domain, our x values, and our range over here are our y values, or f of x values. And the reason that this is a function is because every x maps onto only one y. You can see each x goes only one place. Only one y or only one f of x attached to each of the x values. That's what makes a function. So in contrast, this is not a function because we have an x value that maps onto two different y's, and the x value that's causing the trouble up here is this x sub 1, and that maps two different places. It maps to f of x1 and f of x sub 2, which can't happen and still be a function. So this mapping does not represent a function. Okay, what we can do with a graph is we can use the vertical line test. So here's our friend the parabolic function, y equals x squared. Anywhere we drop a vertical line, if we can touch the graph more than one time, it's not a function. And as you can tell, as I drop these different vertical lines in, this is going to be a function. However, the relation y squared is equal to x. If I try to do the vertical line test here, you can see I'm going to hit the graph here and here with this vertical line, and in an infinite number of places, anywhere I would drop a vertical line, I could hit that more than one time, which means by the vertical line test, this one is certainly not a function. Okay, function notation, I know that you remember this. This is just a quick review. So we're going to let f of x be 3x plus 2, and we're going to define g of x to be negative 4x plus 5. I'd like you to take a couple of minutes and just find f of 3, f of 0, f of negative 2, and g of 3, g of 0, and g of negative 2. So please pause the video here and find those function values, come back and check your answers. Okay, here we go. F of x is 3x plus 2, so these are the function values you should have calculated. F of 3 is equal to 11, f of 0 is 2, and f of 3 is negative 4. And on the g side, g of 3 is negative 7, g of 0 is 5, and g of negative 2 is equal to 13. Okay, now let's talk about interval notation. We need to discuss using both inequality notation and interval notation with the parentheses and the brackets, and how to use those interchangeably. So here we have open interval AB, going from A to B, not including A or B on either endpoint. So the inequality notation, we would have A is less than X is less than B. Or if we're going to use interval notation, we would have A to B in parentheses, the parentheses of course meaning open interval not including those endpoints. So right here next door you can see that now we've closed the interval here at the end at A, so we're now going to include A, which means in our inequality notation we need a less than or equal to when we're talking about A. Still just a less than for B though, because the B endpoint is still open. And then in our interval notation, we're going to have a bracket here at A, bracket indicating a closed endpoint or an inclusive point to an open parenthesis B. Down here at the bottom, closed interval AB means we are including both endpoints. A and B are both solutions to this inequality. So we're going to have less than or equal to for the A and for the B when we're using the inequality notation, and then we're going to have both closed square brackets when we're using interval notation. And then here we have open at A, closed at B, so we have our less than or equal to for the B because that's included, and also we've closed the interval. We've used the square bracket at B to include that endpoint of B. We're going to have some of our intervals that are going to include infinity when we have things that just do not stop. So first we have the graph of all real numbers here. You can see everything is shaded, both sides of A, including A, so the set of all real numbers. So that would be negative infinity is less than x is less than infinity. So x can be anything in between negative infinity and infinity. Or using our interval notation, we have negative infinity, comma, infinity, going from negative infinity to infinity. And then here we have an open interval at A. We're looking at all numbers that are greater than A. So we have x is greater than A, or open at A up to infinity. And just a note for you, sometimes this can be a little bit confusing about why do we not put a square bracket at infinity if we're going to infinity. And the best explanation for that is because when an interval involves infinity, it's an open interval, because when we close the interval, that indicates the end point or the stopping point of that interval, and obviously infinity does not ever stop. So there is no endpoint. So if you have an interval that includes infinity, make sure that you use those open parentheses and you don't try to square that off and close the interval, because that really can't happen. Of a function. So domain, of course, is our x values. And if we look at our function here, it appears that for every x value, we do have a function value everywhere except right here where x is equal to 0. So our domain can be anything except for 0. So a couple of ways to write that. Our domain is the set of numbers x such that x is not 0. Or we can use interval notation. Our domain goes from negative infinity to 0, not including 0. Union means and. 0 up to infinity, again open here at 0, so we're not including 0, but we're including everything from negative infinity to infinity with the exception of 0. Okay, let's take a look at our ranges. Those are our y values. We seem to have a y value everywhere again, except when y is equal to 0. So our range is going to look very similar to our domain, except of course that we're talking about our y values here. So all y's such that y is not 0, or that same negative infinity to 0, union 0 to infinity, not including 0 for our range here. Okay, our second function here, this looks like it's probably our square root function. We have a domain of all of our x values from 0 out. You can see over here where x is negative, we have no x values here. So we're going to start at 0 inclusively and go out. So all x's such that x is greater than or equal to 0, or using interval notation, we're going to include 0 and we're going to stretch that out to infinity. So from 0 to infinity. Let's take a look at our ranges. Our y value also happens to be the same thing. Our function is not defined down here in the negatives, but it is defined starting at 0, and of course going up. If we were able to extend our square root function out longer and longer, of course we would eventually hit all of these y's up here in the range. So our range is also going to be all y values that are greater than 0, or in interval notation we're going to include 0 and go up to infinity. Okay, you can also check out example 3 on page 15 as well if you want another look at some domain and range from a graph. Okay, next we're going to talk about symmetry and even or odd. So here's a picture of a function for you. It's 0.5x to the 6th minus 2x to the 4th. And this is what we call an even function. And what makes a function an even function is when the left half of the graph is a mirror image of the right half of the graph. So you can see this here right half is being mirrored over here on the left half. When that happens, that's called being symmetric about the y-axis. And also if you're trying to check it algebraically instead of just looking at the graph, the rule for an even function is f of negative x is equal to f of x. So over here, f of negative 2 is the same value as f of 2. You can see they have the same function value at both negative 2 and 2, and when f of negative x equals f of x, that's indicative that we have an even function. So let's take a look at this guy here. This is an odd function, and an odd function is what we call symmetric about the origin. And you can tell something is symmetric about the origin if you take the right half of the graph, and if you were to mirror it on the other side of the y-axis like it was even, but instead of it going up, it goes down, it gets flipped upside down. That's what we call symmetric about the origin. So the right half is not a mirror of the left half, but rather it's an upside down mirror on the left compared to what you have on the right. So that's what an odd function looks like. And if you'd like to check it out algebraically, that means f of negative x is the negative of f of x. So if I look here at f of negative, let's see, that's probably negative 2, I want to say. That is the negative of f of 2. Instead of being over here, they're being the same thing. It's down here, it's the negative of it. So if f of negative x is equal to the negative of f of x, then that's indicative that we have an odd function. Okay guys, I want you to try it out for yourself. We're going to determine if the following functions are even, odd, or neither. And I want you to do the math. We're going to see if f of x is equal to f of negative x, which would make it even, or if maybe f of negative x is equal to the negative of f of x, making it odd. And if neither of these things are true, then the function is neither even nor odd. So please jot these functions down in your notes. Take a few minutes and determine whether or not you believe they're even or odd. Pause the video, and then when you come back, I'll have the answers for you. Okay, let's check in and see how you did. First one, f of x equals x squared. That is an even function. Negative x squared is equal to x squared for all x. Next one, f of x equals x squared plus 1, also even because negative x squared plus 1 is equal to x plus 1 for all x. Third one, our linear function, f of x equals x, is odd because negative x is equal to negative x for all x. And then lastly, f of x equals x plus 1. That is neither even nor odd. Let's see, f of negative x plus 1 is not equal to f of x plus 1. And then negative x plus 1 is not equal to the negative of x plus 1. So f of x is not equal to f of negative x, and neither is f of negative x equal to the negative of f of x. So that last linear, f of x equals x plus 1, is neither even nor odd. Okay, these are the homework questions for the first half of section 1-2, pages 18 and 19, numbers 5 to 29, the odds, and then 37, 38, 39, and 40. Good luck. If you get stuck or need any help, please feel free to email me at school, paulym@brsd.org. Okay, we'll see you for the second half of section 2.